Alright, boys and girls, welcome to our very first video lesson in Chapter 6. Our lesson on polygons, shapes, quadrilaterals, shapes, polygons, quadrilaterals. Okay, take a couple quick minutes here and write these definitions down into your notes. I'll read them to you while you're writing. That way you're not just listening to blank space. So a polygon is a simple closed figure made up of line segments. This we remember from Chapter 1. A regular polygon, you know, but it's a polygon with all angles and all sides are congruent. A concave polygon is a polygon with one or more of its interior angles greater than 180. In other words, one of the sides or one of the corners is bashed in. A convex polygon is a non-concave polygon. It's a polygon with all interior angles less than 180, or all with no interior angle greater than 180. So none of the corners have been bashed in. And a diagonal, this may be new, but a diagonal is a segment drawn from any vertex to any non-adjacent vertex in a polygon. So take a couple of minutes, write those down, and I'm going to go grab a cup of coffee. Okay, let's look at some examples of polygons. This is a triangle right here. It would be triangle ABC, or as we know, triangle ACB. It can go in either direction, either clockwise or counterclockwise, going around the triangle. Here's a quadrilateral. It would be DEFG, or if you want, GFED or GDEF, but it could not be D, jump over to F, to G to E, because I can't cross through. I got to go in order, either clockwise or counterclockwise. Here's an example of a non-convex polygon or a concave polygon, because this angle at K is bashed in. It's greater than 180 right here. This is an example of a hexagon. These are some shapes that are not polygons. This first one is not a polygon because it has a side that is not a straight segment. It has a curve to it, so it's not a polygon. This is not a polygon because it's open. It's open right here. If you had cattle inside here, the cattle could get out. So that's open, so it's not a closed figure. Remember, a polygon is a simple closed figure made up of segments, not made up of segments, not closed. This is not simple because it crosses. Two lines cross, so therefore it's not a simple closed figure. It's a closed figure, but it's not simple. This is a polygon, or this is both a polygon and a knot. The whole thing taken together as RSTRVU is not a polygon because it's not simple. But I could go around right here starting at SRSTUV would be an example of a pentagon. Okay, these first three polygons up here are example of convex polygons because all of the interior angles are less than 180, less than 180, less than 180, less than 180. These are all less than 180, while down here, these are some examples of concave polygons or non-convex because yes, some of the angles are less than 180, but this one has an angle that's greater than 180 on the inside. Greater than 180, greater than 180. This angle right here is greater than 180, so these are what we call concave or non-convex polygons. Okay, let's talk for a minute about the sum of the interior angles in a polygon. We already know from chapter 2 or 3, I think it was chapter 3, we discussed that the interior angles of a triangle add up to 180, and we prove that using alternate interior angles. We know that angles 1, 2, and 3 add up to 180 because they make a straight line. 4 is congruent to 1. 5 is congruent to 3 because they're alternate interior angles, and if these two lines are parallel, then the alternate interior angles are equal. So therefore, if 1 plus 2 plus 3 is equal to 180, 2 plus 4 plus 5 must also equal 180 because 1 is congruent to 4 and 5 is congruent to 3. Now let's look at the quadrilateral right here. If I draw this diagonal from one I got hit the right spot. Draw that diagonal right there. I now have divided my quadrilateral into two triangles, one right here and one right here. So I have two triangles whose angles each add up to 180. So 180 plus 180 is equal to 360. So the angles of a quadrilateral are equal to 360. If I take this pentagon, I'm going to draw in a couple of diagonals right now. Let me get my pen out. Here's one. Okay, I'm going to draw one diagonal right here. And from the same vertex, draw another diagonal. And now I can say I have 1, 2, 3 triangles in that pentagon. 3 times 180 is 540, or there's 540 degrees in a pentagon. I can draw diagonals in a hexagon. 1, 2, 3. I now have 1, 2, 3, 4 triangles in a hexagon. 4 times 180 is 720. Okay, so in a heptagon, 7 sides, I can draw diagonals. There's 1, 2, 3. I've drawn 4 diagonals, which leaves me 5 triangles. The 5 triangles are right here. 1, 2, 3, 4, and 5 triangles. 5 times 180 is 900. So there are 900 degrees in a heptagon, a 7-sided figure. You guys right now draw your diagonals in the octagon. Figure out how many triangles and how many degrees there are in an 8-sided figure called an octagon. Go ahead. So you should have noticed as we were working on our different shapes there, each time we added one side to the triangle, we added one more triangle when I drew our diagonals. So starting with a triangle, the sum of the interior angles is 180 degrees times 3 for the triangle minus 2, because I make one triangle and one triangle. In the quadrilateral, we had 2 triangles, so 180 times 4, the number of sides, minus 2. 180 times 2 is 360. Each time we added a side to our polygon, we added a triangle inside, so we added 180 degrees. So how many degrees are there in a 22-sided polygon, a 22-agon? I'm going to do 100, ooh, I need my pen. I'm going to do 180 times 22 minus 2, which is 20. So 180 times 20 is going to be 36, followed by 2 zeros, 3,600 degrees in a 22-sided figure. You guys do this one right now. How many degrees are there in a 25-sided figure? A 25-agon. Very good. You should have found that we're doing 180 times 25 minus 2 is 23. 180 times 23 is equal to 4140 degrees. That's a degree. Okay, you just want to make sure these are written down into your notes. I don't want you to memorize these per se, but you want to kind of familiarize yourself with these multiples of 180, because all the interior angles of any polygon is always going to be some multiple of 180, starting at triangle at 180 and working our way up to decagon at 1440. If I had an 11-sided polygon, I would add 180 to 1440 and get 1620. What happened in 1620, folks? Okay, let's talk about the number of diagonals in a polygon. If we have a triangle, and again, remember, a diagonal is a segment joining any 9 consecutive vertices. In any triangle, every vertex is adjacent or consecutive to any other, so there are actually no diagonals in a triangle. In a quadrilateral, there are 2. 1 and 2. So there are 2, let me put that right here, 2. In a pentagon, we're going to find there are 5, and let me show them to you right here. There is 1 in green, 2 in purple, 3 in red, 4 in blue, 5 in yellow, and you can see now we already counted this green one, we already counted this blue one and the purple one, okay, and we already counted the yellow one and the red one. So there are 5 diagonals in a pentagon. Okay, in a hexagon, you're going to find that there are 9 diagonals. You can see there are 3 drawn from each vertex. So if I look at this vertex right here, there's 1, 2, 3. From this vertex, there's 3 more. 1, 2, and 3. From this vertex, there are 3 more. 1, 2, and 3. But you're probably saying you already counted this one. So there are going to be 6 vertices. So I'm going to write that down. 6 vertices, 3 drawn from each one. But I'm going to divide that number by 2 because I don't want to count the same diagonal twice. In other words, I counted this blue one when I went from this vertex to this vertex. I don't want to recount it going in reverse. Okay, so this would leave me with 18 18 divided by 2 diagonals in a hexagon. In a heptagon, there's going to be 14 because I have 7 vertices. You can see now I'm drawing 4 diagonals from each one. And the reason it's 4, it's 7 minus 3, because I don't draw to myself. In other words, if I were a vertex right here, I don't draw to myself, and I don't draw to the 2 adjacent ones, but I do draw a diagonal to each of the other 4. So it's 7 times 4, and then divide by 2, because I don't want to count the same diagonal twice. For example, I don't want to count from this diagonal, and then backwards again from this diagonal. Count the same diagonal twice. So the formula for the number of diagonals in an n-sided polygon is D is equal to n times n minus 3 divided by 2. So we have the number of vertices times the number of diagonals drawn from each vertex divided by 2, because we don't want to count the same one twice. How many diagonals are there in a 22-sided polygon? We're going to use the formula D is equal to n, which in this case is 22, times 22 minus 3 is 19. We're going to take that number and divide it by 2. And we should get 209. 11 times 19. You guys try this one. How many diagonals are there in a 25-agon, a 25-sided polygon? Go ahead and do your math. Okay, you should have gotten 275 because we did 25, the number of vertices, times 22, the number of diagonals drawn from each vertex, and then we don't want to count each diagonal twice, so we divide by 2, which is 25 times 11, 275. Alright, this is my favorite formula. The sum of the exterior angles in a triangle, sum of the exterior angles in any polygon, no matter how many sides the polygon has, is always 360. So how many degrees are there in the exterior angles of a 22-sided polygon? The answer is going to be 360. You guys try this one. How many degrees are there in a 28-sided polygon in the exterior angles? Write down your answer. Very good. You get 360. Alright, boys, girls, we are almost done. Let's do a couple more problems here. Find the sum of the measures of the interior angles of a convex heptagon. Again, heptagon means 7 sides, so we're going to use the formula. Sum of the interior angles is equal to 180 times n minus 2. And in this case is 7, so I have 180 times 7 minus 2, which is 5. 180 times 5 is 900. Okay, find the measures of each interior angle of the quadrilateral ABCD. So this is a quadrilateral ABCD. So we know that the sum of the interior angles is 360. So we can look here, we have x plus 3x plus 90 plus 90. Those are both right angles, is equal to 360. Let's combine our x's. X plus 3x is 4x. Plus 90 is 180, is equal to 360. Subtract the 180 from both sides. I get 4x is equal to 180. Doing my math wrong there. 180. X is equal to 45. So therefore, one of these angles at D is equal to 45. This one is at A is equal to 3x, which is 3 times 45, 135. And these are both 90. Okay, let's do this one. Tenths. The poles for a tenth form the vertices of a regular hexagon. Hexagon means 6 sides. I'm going to draw a picture. This is a regular hexagon, which means all angles are equal. When the poles are properly positioned, what is the measure of the angle formed at the corner of the tenth? We're looking for one of these angles right here. I know that I have a hexagon, so I know that my formula for the number of interior angles is going to be 180 times n minus 2. Well, n is 6, so I have 180 times 4. 6 minus 2 is 4. So the number of angles, the sum of the angles is equal to 180 times 4, which is 720. But now, all 6 of these angles added up equals 720. Well, if it's a regular hexagon, each angle is equal, so I'm going to take that total number, divide by 6. 720 divided by 6 is 120 degrees, is this angle, and all of the angles of my regular hexagon. Okay, in this problem right here, we're going to do some more algebra. The measure of an interior angle of a regular polygon is 135 degrees. Find the number of sides in the polygon. So we're going to solve for n. Well, I know that the sum of the interior angles is equal to 180 times n minus 2. Then if I want to find the measure of each angle, I'm going to divide that whole thing by the number of vertices, as that's the number of angles, divided by n. So I now know that the one of the angles is 135, and that is equal to now 180 times n minus 2 divided by n. I'm going to multiply both sides by n. So I have 135n is equal to, and I'm going to distribute my 180. So I have 180n minus 360. Okay, I'm going to subtract the 135n from both sides. I'm going to add the 360 to both sides. So add the 360. Okay, on this side, the 135n minus 135n, they cancel. I get 360. That's just 60. Is equal to 45n. Divide both sides by 45. N is equal to 360 divided by 45, which is 8. So the number of sides in my polygon is 8. This is an octagon.